Hi, welcome to Expertisor Academy. This is Giri, lecturer in physics. In this video, we discuss about the deviation angle for combination of lenses. The equation delta is equal to h by f. That is the deviation angle. H represents the height of the point of the light is incidence on the lens. So the distance from optic center to point of incidence of the light. So this equation tells that angle of deviation is the ratio of height to the focal length. Now, case of two lenses of focal length f1 and f2 arranged coaxially but separated by a distance t can be considered as the shown in the figure. So this figure I will show it in next slides. So the focal length is the f1 and f2 for two lenses. For a parallel ray that falls on the arrangement, the two lenses produces delta 1, delta 2 deviations respectively, and the net deviation is delta. Here we discuss the deviation angle for combinations of the two lenses. So that combination be formed as like this. This is the combination of the two lenses. Now we derive the combination of deviation angle. For that, two lenses are in contact. So the sum of the deviation angle for prism lens 1 and lens 2, that is delta 1 and delta 2. Delta 1 is equal to h1 by f1, delta 2 is equal to h2 by f2. So here combination deviation angle delta is equal to h1 by f. h1 by f, that is equal to h1 by f1 plus h2 by f2. From the geometry, h2 minus h1, that is equal to p2g minus p2c. So when you take this combination of lenses at particular separation distance d, in the particular separation distance d, here h2 minus h1, that is equal to p2g minus p2c, that is equal to cg. So h2 minus h1, that is equal to bg tan delta theta 1, that is identically equal to bc delta 1. So h2 minus h1, that is equal to d into h1 by f1. So here h2 is equal to h1 plus d into h1 by f1. Substituting the above equation, so we get h1 by f plus h1 by f1 plus h1 by f2 plus H1 D by F1 F2. And further simplification, 1 by F is equal to 1 by F1 plus 1 by F2 plus D divided by F1 F2. The above equation could be used to find the equivalent focal length. To find the position of the equivalent lengths, we can further write from the geometry. For a parallel ray that falls on the arrangement, the two lenses produces deviations delta 1 and delta 2 respectively. The net deviation is delta. So in this equation, PP2 that is equal to EG that is equal to GC divided by tan delta. So these all relations are taken from only combination of the two lenses separates by a distance d. So here PP2 that is equal to EG that is equal to H1 minus H2 by tan delta that is equal to H1 minus H2 by delta. From equation 6.889 and 6.91, so we get H2 minus H1 that is equal to D into H1 by F1 and delta is equal to H1 by F. We get PP2 that is equal to D H1 by F1 into F divided by H1. PP2 that is equal to D into F divided by F1. This equation is the position of the equivalent single lens from the second lens. Its position from the first lens is PP1 that is equal to D minus D into F divided by F1. PP1 that is equal to D into 1 minus F by F1. So this is the position from the first lens or second lens. So these two equations represents the positions of the first and second lenses. In this video, we discussed the focal length for the combination of two lenses at a distance d that is equal to 1 by f1 plus 1 by f2 plus d divided by f1 f2. At the same time, we found the positions of the two lenses from one to another, that is PP1, PP2. PP1 is equal to D into 1 minus F by F1. PP2 that is equal to D into F by F1. So this is the equations for positions of the two lenses. So here finally we conclude the combination of the lenses, equations for this combination of lenses, especially focal length and positions. Thanks for watching this video. For more videos, visit www.expertisoracademy.com. Thank you.